So this video is the first video of a series of videos for the course Introduction to Analysis. A lot of universities may call this Analysis on the Real Line or Analysis 1. Others call it Introduction to Analysis. I'm going to call it Introduction to Analysis just because, as we see here, the book on the left, well, this one down here, this one is what I'm going to be going off of. It's commonly used in university. And then the one on the right over here, this one is used mostly just for intuition. I don't think a university course actually uses this book to teach it. But this first video is section 0 on, well, the preliminaries we need to know in order to, I guess, have a good understanding on the concepts to come. And that's why it's section 0 and, well, named preliminaries. So without further ado, we go on to set theory. First things we need to know about set theory is, here's a few animations on sets, but the definitions we need to know are, as we can read here, sets, set an element belonging to a set. So here X is an element of A. The subset, we need to know what a subset is. The union of sets, intersection of sets, complement of set, and indexed family. Here we see a green box here. This green box is going to be used for definitions for this video and for every video to come. But those are the definitions we need to know, and the theorems we should be familiar with or should already know are the following. And before I even go over them, as you can see, this blue box, this one, will be used for theorems. It's a darker blue. There will be a lighter blue for proofs, but I'll go over that when we get to it. But here are the theorems where A, B, and C are sets, and I'll just let you look through them. I don't want to waste time just actually describing what they are, what they mean. But they're basic properties of set theory. And finally, De Morgan's laws for sets. And again, you can pause the video, look over them, make sure you're familiar with them. As you should probably, at UTEP, you might have seen this, or you actually should have seen this in Principles of Math, the course. But that's what we need to know about set theory. So if we move on, what we need to know about relations and functions. So first, here's some pictures showing maybe a function, a relation. And as you can see from this picture here, all functions here are relations. So the definitions, we actually don't have any theorems for this slide, just mostly definitions. And you can pause again. I'll just go over them quickly. We should know ordered pair. Cartesian product, this is what I have in parentheses. This X looking symbol is what we use commonly for Cartesian products of two sets. There's a relation, function, domain, image, the converse of a relation, injective or one-to-one, surjective, which is onto, and if something is both of these, then it's bijective. We should know that. It's a one-to-one correspondence. There's a composition of function. Again, this little symbol here, what we use to denote composition of functions. And, well, we should be familiar with inverse functions. Moving on, we should be familiar with mathematical induction and recursion. Now, on the previous slide, we had definitions and no theorems. In this slide, we have only theorems and no definitions. We should be familiar with the well-ordering principle, which says that every non-empty subset of n, or the natural numbers, has a smallest member. We should be familiar with the principle of mathematical induction, sometimes abbreviated PMI. So here, if P of n is a statement containing the variable n, such that P of 1 is a true statement, and that for each k in n, if P of k is true, then P of k plus 1 is also true. So then P of n is true for all n in the net, or n being a natural number. That's the principle of mathematical induction. You should have already done exercises with that. But then there's also a second one, which is sometimes called a strong principle of mathematical induction. In this case, we're just calling it second. That's the statement. So here, it's just that P of n is a statement concerning the variable n, and so on and so forth. I'm not going to, again, go much into detail because these are preliminaries. And then just a little comic you can pause and read over involving mathematical induction. The next thing we should know is equivalent and countable sets. This you may have not gone over too much. Not a difficult concept, but here I put these images first, see if you may recognize this. Here, for example, in this picture here, we first have the, I guess I should have done this. Let's see. So these are the even numbers, right? And then these other ones are the odd. So the odd integers, non-negative integers, and the even integer, or yeah, non-negative integers. This is a symbol called aleph not. Maybe you recognize it. Over here, the second one, it's used for a proof, or at least for intuition of a proof. Maybe you know what that is, but it's a proof showing that the real numbers are uncountable. So let's go over some definitions we should be familiar with. Equivalent sets, again, this symbol denotes equivalent sets. We should know what finite means: countable, countably infinite, and uncountable. And the few theorems we should know is that if A, B, and C are sets, and we have a function f that maps A to B, and it's an injective function, and G maps B to C, and it is also an injective function, then the composition G of f is injective. And this not only works for injectivity, or one-to-one, it's also for surjections, for surjective functions, and it also works for bijective functions. Right, so we should already be familiar with this. Maybe you even saw them in another class. Then there's this other three little theorems. If let A, B, and C be sets, then A is, so what does this little thing mean? Well, that they're equivalent sets, as we see up here. That they're equivalent sets. So A is equivalent to itself. If A is equivalent to B, then B is equivalent to A. And if A is equivalent to B and B is equivalent to C, then A is equivalent to C. And these three properties give us something. It tells us something about this relation right here, the equivalent set relation. It tells us that it's an equivalence relation. It's kind of, well, as you can probably see, it's almost pretty much in the name. And then finally, just some little comic. Again, you can pause and read. Moving on to the last thing are the real numbers. And this one, we don't really go over them. If you really, there's other books you can look for to actually show that the real numbers do exist. Here, we kind of just assume that they do exist and get some properties from them. Right, so first I'm going to start off with the pictures. Here, the distance between x and y on the real line. We use this called the absolute value, but it's our metric here to show the distance. So the distance from x and y is the absolute value of their difference. And here you should know that this set denotes the real numbers. Down here, there's the density property. You should also be familiar with that. And then here are just some terms we're going to go over, but again, that you should already know. So the definitions is an ordered field. If you know what an ordered field is, then you probably know that the real numbers are an ordered field. We should know bounded from below, bounded from above, the min or minimum, minimum, and maximum. There's infimum and supremum. And again, this picture down here pretty much shows an example of what each of those are if you don't already know that. So for example, this first line, we're going to focus on this real line. So we have this open interval, our supremum, this red dot here. It's the least, as they call it, the least upper bound, right? Because there's this upper bound, there's this one, there's also this one and this one. But this is, out of all our upper bounds, this is the least of them, or the smallest. And the greatest lower bound is, as you might know, called the infimum. So again, of all these little lower bounds, or of all these lower bounds, this is the greatest, the infimum. Open interval, closed interval, you should know that from high school, middle school. The maximum of a set, this is a maximum because it's a closed interval. So this little point here belongs to the set. That's why it's a maximum. It's the biggest element of the set. Here, this dot is only supremum, not a maximum, because it's an open interval, so it doesn't belong to the set. But again, we should already probably know that. And then going over a few theorems, we should know that if S is a non-empty set of the real numbers that is bounded from below, then S has an infimum. We should know that between any two distinct real numbers, there's a rational number. So what does that tell us? That tells us that the rational numbers are dense in the reals. So against this property over here, the rational numbers are dense in the reals. Between any two distinct real numbers, there's an irrational numbers, also telling us that the set of irrational numbers are dense in the reals. We should know that, well, this is, I guess, intuitive. You can even try to prove it yourself. It's not difficult. If we let x be any real number, then there's an integer n, such that n is less than or equal to x, and n plus 1 is greater than x, right? So for example, here if we let x be 1.5, then n is equal to 1, and n plus 1 is equal to 2. So we can always find this n given any x. Okay? And we have that if p is a positive real number, there is a positive real number x such that x squared is equal to p. So again, that should not fair, I wouldn't say obvious, because we do require proof, but say p, given p equal to, let's say, 3 pi. Then there's a number x such that x squared is equal to 3 pi. And that's pretty much all we need to know to start this course. I hope it's nothing too complicated. Maybe you need to review some things. But yeah, this is a short video, less than 15 minutes, because of the fact that we're just reviewing things. And finally, we have our last theorem here. We have that we let a and b be any real numbers, then all the absolute value is equal to the product of the absolute value of each individual one. Here, if the second one, this here is a variable epsilon. Epsilon, we use it for an analysis. We tend to use it for an arbitrarily small real number. So it makes these properties true given if epsilon is greater than 0, any arbitrarily, or actually any real number greater than 0, then this property holds right here. And for 3, we should know the triangle inequality. And finally, the fourth one, also property. So yeah, that should be it for the video.